Afternoon, engineers.
Afternoon, sir.
How are you?
We are fine, thanks. How are you, sir?
You already know. Today, we will talk about how to determine the value of a resistor to drop the voltage and limit the current in a circuit.
Yes, sir.
What is this?
Voltage.
With the rating of
5 volt.
and
1 amps.
1 amps. Ne?
Yes, sir.
I say, then here we have a red wire going to the LED. Let me just make my LED blue. And this is the black wire back to the battery. Let's assume that my LED rating is 2.2 volt with 20 milliamps.
Yes, sir.
Is the symbol for LED. So now you can see already that if I can try to power this LED using this battery, this much voltage will burn the LED completely.
Yes, sir.
Because the voltage supply is too high, né?
Yes, sir.
As compared to the voltage that the LED can handle. So now we need to put a resistor somewhere here, né?
Yes.
So that, let me use my, okay, I can somewhere use green. Is the resistor, né?
Yes, sir.
So now the current must flow in this direction since it's a conventional current, né? And then get to the resistor. The current coming in to the resistor at this point will be 5 volt. Ne? You remember the story of a water pump and water?
Yes, sir.
When we couldn't adjust the force applied by the pump or the pressure applied by the pump, what did we do? We must pinch the pipe, ne?
Yes,
To reduce the output or the pipe outlet. Ne?
Yes, sir.
So here we're going to do the same thing. Just to remind you, the pipe was almost like this. Ne?
Yes, sir.
There's this amount of water flowing in. Then we had to apply opposing pressure. Yeah. The pressure was just here. Ne?
Yes, sir.
That's where my thumb was. Yeah, let's assume this is my thumb. Ne? I pressed here. So now, when water gets to this point, the flow will must be reduced. Ne?
Yes, sir.
So there'll be small amount of water going in, but there there'll be a little bit out. But the pressure at this side will be less than the pressure at this side. Ne?
Yes, sir.
Here is a little bit big as compared to this side. Ne?
Yes, sir.
Here we need to do the same thing. We need to apply pressure here or opposing pressure to the one that was generated by the motor. Ne? So the amount of water that needs to come out or the amount of force that needs to come out of the resistor must be 2.2 volt. That the LED can take. Ne?
Yes, sir.
The current inside is 1 amp, which is equivalent to 1000 milliamps. Ne?
Yes, sir.
Even that 1000 milliamps will be at this point before the resistor. But now on the output, we need to reduce it to 20 milliamps. Does it make sense?
Yes, sir.
So now what we need to do is we need to find the amount of opposing pressure that we need to apply here in order to reduce this supply into this amount of voltage that can be taken by LED. Does it make sense?
Yes, sir.
Let's try to do it. We will use the law called Ohm's law. Ne?
Yes, sir.
The opposing pressure, which is the resistor, is equal to the input pressure, which is 5 volt, minus the output pressure, which is 2.2 volt. Ne?
Yes, sir.
divided by the amount of current that we want on the other side, ne?
Yes, sir.
Yes. The input voltage is 5 volt from the source, ne?
Yes.
And the voltage that we will get after the resistor must be 2.2 volt, ne?
Yes.
All divided by 20 milliamps. That milliamps is equivalent to, you must go and check your chart, ne?
Yes, sir.
You remember most that the big M was equal to 10 to the power 6, ne?
Yes, sir.
Then the small m is equal to 10 to the power minus 3. So we're going to put 10 to the power minus 3. But we will revisit that chart again, ne?
Yes, sir.
Yeah, now let's look at the value of a resistor that will be suitable for the job. Let me use a calculator. And the answer is 140. What is the surname?
Ohms.
Ohms, ne? Resistor surname is ohms, ne?
Yes, sir.
And the voltage surname is volt. And the current surname? Amps. Ne?
Yes.
You got it. So now the resistor value that we need to put in that circuit in order for the LED not to burn is 140 ohms. Are we done?
Yes, sir.
No, we're not done. So now we will need to determine the color code of this resistor. Because now let's say you're going to the shelf now to look for this resistor. Are you only going to look for the number? If you only going to look for the number, you might struggle, ne? It might take longer. So now you go back to the color codes. What is number 1?
Black, brown.
Brown, ne?
Yes, sir.
So the first color will be brown. This is the first band. And the second band?
Yeah.
Yellow. And the third band?
Black.
It's black. Yeah, black is the multiplier. And the last one?
Gold.
Gold. It won't always be gold, ne? It also depends on the purpose of a resistor, ne? Remember that gold have a wide tolerance, ne?
Yes, sir.
Unlike the color codes. So now it will depend on where is this resistor going to use, how sensitive the circuit is. If the circuit is too sensitive, gold is most 5%, ne?
Yes, sir.
Yeah, it's 5%. There's another one that is 1%, ne? We'll have to check that color. So if the circuit is too sensitive, we're going to use a resistor with the 1% tolerance, ne?
Yes, sir.
But if it's not too sensitive, we can use the one with 5% tolerance, ne?
Yes, sir.
Yes. Now we know the colors. We know the value of a resistor. Now we need to determine the wattage, ne?
Yes, sir.
That current part, ne? Now to determine the power, we can use the following formulas, ne?
Yes, sir.
Either current multiplied by voltage. Power is equal to the square of a current multiplied by a resistor. Or power is equal to square of voltage divided by a resistor, ne?
Yes, sir.
Can you see that? Okay. Let's start with this one. You remember most the voltage you got, ne?
Yes.
It was 2.8 volt, 20 milliamps is equal to 20 minus 3 amps, ne? And the resistor value is 140 ohms, ne?
Yes.
So we have the current, which is this one, the voltage, this one, and the resistor value, which is this one, ne?
Yes, sir.
Now let's see if we use all these formulas, if you're going to get the same wattage, ne?
Yes, sir.
Let's start with this one. Power is equal to current multiplied by voltage. What is the current value? It is 20 milliamps, ne?
Yes, sir.
And the voltage value is 2.8 volt, ne? Let me use my magic machine, ne? and the answer is 0.056 watt. Ne?
Yes.
Let's try another one. We just put the current squared. Ne? We square the current, multiply by 140 ohms. And the value is the same, ne? 0.056 watt. Let's try another one, just to see. P is equal to 2.8 squared divided by 140. And let's see. The reason why I'm showing you all these formulas at the same time now is that if you get only two of these in a circuit, if you have a value of a resistor and a current, you can use this one.
Yes, sir.
If you have a voltage and a current, you can use this one. You still get the same answer.
Yes, sir.
So now that you know that the value of the resistor is 140 ohm with a wattage of 0.056 watt, we can now go get the resistor
Yes, sir.
and plug in this resistor into the circuit, and our LED will be safe.
Yes, sir.
But now the wattage is 0.056, so what size of a resistor are you going to take? You see here we have a 0.0125 watt.
Yes, sir.
Even that one will be okay for this particular circuit.
Yes, sir.
This is the method. Now if I give you a circuit with a high power rating or the high power supply, you'll be able to determine the resistor
Yes, sir.
with ease, because I'll show you how to do it. Now let's turn things around.
Yes, sir.
Now we are going in reverse.
Yes, sir.
Let's say you have a resistor, LED, and a power source. You know that your LED needs 3 volt, 20 milliamps. Your reservoir that you have is 1 kilo ohm with a rating of a quarter watt. Now we are looking for the battery source that can supply this LED without burning the LED. So we need to determine the value of the voltage and the value of the current.
Yes, sir.
Let's see now how do we do that. We know almost that R is equal to V1. V1 is this at this point, minus V2 all over the current value. V1 is what we're looking for, because V1 comes from the battery. We don't have. So okay, let's start with the resistor. You know almost a K, that K is equal to 3 zeros.
Yes, sir.
You remember almost?
Yes, sir.
Yeah, so we have a 1 and a 3 zeros. Then a V1 minus the voltage at V2 is equal to this voltage,
Yes, sir.
which is 3 volt, the voltage you are looking for. And the current is 20. The small m is equal to times 10 to the power minus 3. So we say times 10 to the power minus 3. Does it make sense?
Yes, sir.
So now we'll cross multiply on both sides with this 20 milliamps. So when you say times 20, this one and this one will cancel almost, ne?
Yes,
But you still need to multiply on this side, ne? Okay?
Yes, sir.
Now if you times these two, we'll get a 20, ne? 20 is equal to V1 minus 3 volt. Therefore, V1 is equal to 23 volt, ne?
Yes, sir.
So the voltage at this point is equal to 23 volt. And in essence, the source voltage will be 23 volt, ne?
Yes, sir.
And the current that we need for the LED, we already know that is 20 milliamps, ne?
Yes, sir.
So we bring back 20 milliamps. Are we done?
No, sir.
No, we're not done, eh? Now we need to check or to confirm that this resistor that we have will be able to withstand the power generated by the source, ne?
Yes, sir.
So now we will say P is equal to current multiplied by voltage, ne? Our current is 20 multiplied by 10 minus 3 multiplied by 23 volt, ne?
Yes, sir.
The voltage is equal to, let's set it quickly. And the wattage I'm getting is 0.46 watt, ne? And this one is equal to 0.25 watt, ne? Can you see that?
Yes, sir.
The wattage that will be produced by the battery is more than the wattage that the resistor can handle, ne?
Yes, sir.
That is engineering. Just because you got all these values doesn't mean that you are good to go, ne?
Yes, sir.
You need to confirm. So this resistor is not the right resistor for the job, ne?
Yes, sir.
This resistor will burn because the wattage that is generated by the power is greater than the wattage that this resistor can stand, ne?
Yes, sir.
So we need to use a little higher wattage, ne?
Yes, sir.
What comes after quarter watt? You can just use 1 watt, ne?
Yes, sir.
And we are good to go. This circuit will now work perfect. That's what engineering is all about, ne?
Yes, sir.
Does it make sense?
Yes, sir.
Now let's do practical and see if what I just calculated on the board will correspond to the practical things, ne?
Yes, sir.
Do you remember that the LED, ne, required what is it, 2.2 volt, ne,
Yes, sir.
at 20 milliamps? Even though here is 24 milliamps, but it's still fine, ne?
Yes, sir.
You see that it's lighting, ne?
Yes, sir.
Let me switch off the light so that you can see clear. Can you see that?
Yes, sir.
Now, what do you think will happen if I increase the voltage? What will happen?
Will light more.
No. What will happen?
It will burn.
Let's see if it's going. It will burn. I also say it will burn. Let's see if it will burn. And it's gone. At 20 volt, it just died, ne?
Yes, sir.
Let me switch on the light. Did you see that?
Yes, sir.
Now let's say now we have 12 volt, ne?
Yes, sir.
We have 12 volt. And we need to power another one. If I put in another one here, even that one is going to burn, ne?
Yes, sir.
Because it only operates at 2.2 volt, ne?
Yes, sir.
So now I'll need to put a resistor. I already calculated prior to this, ne?
Yes, sir.
560 will work fine, ne? Now I put in a resistor. Put in my red LED. Now why does LED don't light now? Oh, I swapped the polarity around. You see, with the resistor at 12 volt, 10 milliamps, it's working just fine.
Yes, sir.
No, I'm just trying to demonstrate what we're calculating on a board.
Yes, sir.
Yeah, I'm not going to demonstrate the power dissipation.
Yes, sir.
But you see how it works.
Yes, sir.
So now if I increase the voltage, what's going to happen?
To bend
Bend what?
the resistor.
Let's see. I'm at 20 volt, 25, and I can smell something. Let me keep going. 30 volt. I can see smoke. Can you see smoke coming up?
No, sir.
The smoke coming up. The resistor cannot take that voltage anymore. Let's increase the current as well. See, it's burning.
Yes, sir.
The resistor say I can't take this anymore, but it's still hanging in there.
Yes, sir.
So now to avoid this, what must we do? When we increase the voltage, we must recalculate the value of a resistor.
Yes, sir.
Because now let's assume this was inside the circuit that you overpowered. What's going to happen? It will burn the equipment and burn your house,
Yes, sir.
or burn the power plant. Let's keep going. 40 volt. Let's see, Mr. Resistor, if you can still take it. Can you see the smoke?
Yes, sir.
It will burn open.
Yes, sir.
Now the resistor is gone at 45 volt.
Yes, sir.
You see the LED is still alive.
Yes.
Only the resistor that bent.
Yes, sir.
The resistor, the LED is still alive. So now it is your own baby to go and calculate that at let's say 30 volt. What was the amount of resistor that we needed to put here in order for the resistor not to bend?
Yes.
Do you understand?
Yes, sir.
Are you happy?
Yes, sir.
Now, from all this, what can you tell me about the resistor? Oh, it bent my board as well, but it's fine. I told you that the resistor, we put the resistor in a circuit to protect the LED.
Yes, sir.
So the resistor had to bend, but the LED is still there. But you don't just take any value of a resistor and put it in there.
Yes, sir.
Because sometimes when the resistor bends, it catches fire. So you need to sit, do the calculation, get the right amount of resistor that you're gonna need for the circuit.
Yes.
If you put a small resistor for that power, if it fails to handle that power, it's going to burn. If it's too much, it will let a small amount of current to pass through.
Yes, sir.
So your LED won't shine that bright.
Yes, sir.
Let's see if I put 10 kilo ohm. No, it's not gonna burn. It's too big. You see that your resistor don't even shine.
Yes, sir.
Why? The resistor is too big.
Yes, sir.
Yes. The bigger the resistor, the lesser the current that is allowed to pass.
Yes, sir.
So it is important to sit down and calculate the value of a resistor, the wattage, and then you can place the right resistor for the right circuit.
Yes, sir.
The class is adjourned. Until next time, ne?
Yes, sir.
Bye.